Hi, and welcome to this presentation of our SOC paper, Explainable Machine Learning in Adversarial Environments. My name is Max, and this is joint work together with Christian Resneger. I want to start this presentation with an example. Let's consider this image of a bird. Can you guess what the prediction and the explanation of this photo might look like? It is a frog, and the explanation is this square. This cannot be correct. You might have figured out that this is an adversarial example. You can also see it in the noise in the input. But in addition to the prediction, it is also fooling the explanation method CredCam to show the square. Please note that this attack can also be executed for other explanation methods and arbitrary target explanations. This is just one example of an explanation-aware attack. In our paper, we consider attacks against explainable systems in general. But let me first show you what an explainable system is. On this slide, we depict the explainable system S. It consists of a classifier F and the explanation method H. The prediction is produced by the classifier, which is trained on a dataset D. The explanation is produced by an explanation method and depends on the model and the input. In the explanation at the bottom right, you can see relevant pixels in yellow and unimportant pixels in dark blue. In our paper, we have identified 3 attack vectors that are used in recent papers to perform explanation-aware attacks. First, we have seen input manipulation attacks, similar to the example we showed you on the first slide. Then we found model manipulation attacks. These can happen at different levels. There are data poisoning, code poisoning, and model poisoning attacks. In the prediction-only settings, where the effects on the explanation methods are simply ignored, we can see mainly backdooring attacks as model manipulations. In explanation-aware attacks, we also saw attacks that keep the model completely intact prediction-wise, but make the model show unusable explanations, for example. Lastly, we found system manipulation attacks. Here, the adversary is the operator of the explainable system and can do anything that produces a prediction and an explanation. For example, one work used an unfair model for the prediction and some fair models to generate the explanations in order to fair wash the system. As said, we denote attacks that ignore the explanation as prediction only, as displayed on the left. On the other hand, we use the term explanation aware for attacks that consider the explanations. We have identified 3 different attack types of explanation-aware attacks. First, there are explanation-preserving attacks, where the adversarial aim is to preserve the explanation but fool the prediction. This type is applicable, e.g. to hide an ongoing backdooring attack. Here the explanations would highlight a spatial patch trigger as relevant. Explanation-preserving retains the original explanation without the highlight on the trigger and can thus potentially bypass defensive techniques. Next, we found prediction-preserving attacks. Here, the attacker only aims to change the explanation, but keep the prediction. In our study, we found that most works use this setting. The application scenario will be to mislead an auditor who tries to find out if the system is fair or not. Finally, we have dual attacks, in which both the prediction and the explanations are under attack. This attack type is particularly helpful if the explanation method is class-specific. As the prediction is now changed, the adversary might want to show an inconspicuous explanation of this new prediction. In the prediction-preserving and the dual case, the goal was to alter the explanation. We found 3 different ways in which an adversary might want to alter explanations. The naming scheme is similar to the one used in prediction-only attacks. In prediction-only attacks, however, the label is just a scalar. The explanations, on the other hand, are high-dimensional, giving us more possibilities. In this slide, we have visualized 2-dimensional explanation spaces for simplicity. First, we have untargeted attacks, where the explanation of the manipulated input or the manipulated model should be maximally different from the explanation in the clean scenario. The concrete similarity can be measured according to multiple different distance metrics. And then we have found targeted attacks. Here, the malicious explanations should all be equivalent to one specific target explanation. Here we again visualize the square, but in principle it could be anything. Lastly, we have identified semi-targeted attacks. Here the target explanation for a given sample is a function of the clean explanation. On the slide we visualize an inverting function, but in principle any function in the explanation space can be used. According to these three dimensions, attack vector, attack type and scope, we classified the relevant literature. You can find the input manipulations attacks on the left and the model and system manipulations on the right. Interestingly, most works only consider one of the attack types. We conclude from this that the concrete attack scenario is heavily depending on the application. Also, we found that most works focus on gradient-based explanations. After this overview on the literature of attacks, we investigated different defensive strategies. We started with defenses at training time. There are four major directions in which defenses have been proposed: data validation, using robust model architecture or training procedures, and finally validation techniques that apply after the model is trained. In our paper, we discuss each of these points in detail concerning explanation-aware attacks. Next, we have considered operational defenses that apply at inference time. Here we have input manipulation, model monitoring, and input-output validation. Note that the first two also apply to prediction-only attacks, while the input-output validation is particularly relevant against explanation-aware attacks. The additional output, the explanation, can be validated in relation to the predictions of the system. In our paper, we investigate each of these approaches with explanation-aware attacks in mind. Optimally, the model that results from our training time defenses is already robust against explanation-aware attacks. But what does robustness against explanation-aware attacks mean? In our research, we found that the term attribution robustness or attributional robustness is overloaded and can mean different things. Therefore, we provide a hierarchy of formal robustness notions. As you can see in blue, different papers already use the various robustness notions. We don't want to go into detail of the notions here. If you are interested, please have a look at section 5 in our paper. We now want to conclude this short video in our paper. With our paper, we primarily want to make aware that defense techniques based on explanations can potentially be bypassed by explanation-aware attacks. Also, we found that there are many open research questions in this field. You can find some of them pointed out in our paper with little boxes. Finally, we found that actual adversarial incentives are very dependent on the application. We thank you for watching this video. If you want to learn more, please refer to xaisec.org or write me an email at noppel@kit.edu. Thank you.